This is Zhiyuan. The topic of my presentation is security analysis of Algorand smart contracts. So what is Algorand? Algorand is a new generation of blockchain launched in 2019. It is the first blockchain that provides immediate transaction finality. In the following, I will first give a brief introduction to Algorand smart contracts. Next, I will describe the vulnerabilities we found in Algorand smart contracts, and then elaborate on the automatic detection tool. Finally, I will show the evaluation results and give some interesting case studies. In Algorand, there are two types of smart contracts, stateful and stateless. The stateful smart contracts represent applications that reside on the blockchain and are remotely callable. A stateful smart contract is composed of two programs that are the approval program and the clear state program. The approval program is used to handle the main logic of the smart contract. The stateless smart contracts are also known as smart signatures. It is different from the stateful smart contracts because the state storage and the inner transactions are not allowed to be used in them. Generally, a smart signature is accompanied by a transaction, and its logic is used to determine whether the transaction will be approved. The given example code shows a smart signature that checks the transaction type, transaction phase, transaction amount, and some other critical parameters. To facilitate the development of smart contract-based applications, Algorand introduced some new features. However, the new features also enlarge the attack surface of Algorand smart contracts. In this study, we performed an analysis of the Algorand platform and found 5 types of generic smart contracts vulnerabilities. Okay, the unchecked transaction fee and the unchecked transaction parameter vulnerabilities, both resulting from smart signatures failing to validate the transaction parameters. If the transaction fees are not limited, an account can be depleted by a high-fee transaction. Similarly, if the RK2 parameters is not checked, an adversary can set the RK2 parameter to his public address, and then he will take over this signature account. Next, the unexpected delete and update vulnerability. The Algorand smart contracts can be updated, and the owner of the contracts can initiate a special type of transaction to upgrade the smart contracts. Note that anyone can send the application update transactions and the application delete transactions, and whether the transaction is approved depends on the program logic. If there is a programming error in the smart contracts, it may result in anyone being able to update or delete the smart contract. The last is the unchecked transaction receiver vulnerability. It occurs when developers incorrectly assume that all transaction receivers are current application. If receiver validation is omitted in payment or asset transfer transactions, an attacker can self-appoint as the receiver, and as a result, disrupting the program logic. Okay, we built Panda, an automated tool for detecting the aforementioned vulnerabilities. It takes user defined settings and an application ID as input, then retrieve the program bytecode and the global state from the blockchain. This bytecode is disassembled into a tier program. The global state is stored as symbolic arrays in the memory model. The safety builder creates a control flow graph from the tier bytecode. The memory model keeps the symbolic arrays for the symbolic executor, which includes an opcode handle registry and an executor. Each opcode handle is a Python function. The analysis plugin have a registry for vulnerability detection rules implemented at the individual functions. When a feasible path is found during symbolic execution, these functions are called to detect vulnerabilities. Detecting and verifying smart signature vulnerabilities is straightforward, but complexity increases when a validator is included. Validator is a set for smart contracts specified in the smart signature, and both involve transaction parameter checks. To overcome this, we use the bytecode rewriting to merge the smart signature and the validator into a new smart signature before constructing the control flow graph. We first identify the validator's application ID and download its bytecode. Then we rename the smart signature's jump labels to avoid name conflicts. Next, we replace all return instructions in the smart signature with the BNZ instructions, directing execution to the validator's entry point upon reaching the end of the smart signature. Lastly, we create a new smart signature by concatenating the smart signature and the validator. Once done, this new smart signature undergoes further process to construct the control flow graph. Since Algorand has two different data types, we need to adopt some new techniques to deal with data type related issues. It is worth noting that we develop a new method named asynchronous type bounding to determine the variable data type. When reading data from the blockchain, we set the data type to unknown. Only when the executor uses the data later and there is an opcode can assist in determining the data type will be finally determined. The next part is the vulnerability detection rules. We define 4 predicates to accurately express the vulnerability detection rules. To be specific, the predicate P is true if new path constraints can be added while keeping the constraint set stable. The predicate Q is true if the current path constraint does not contain any variables from the parameter set. Predicate R is true when the current execution trace uses at least one opcode from the parameter set. And finally, the predicate I is used to check the implicit type of a transaction. The detection rules are complex, and here I only show the detection rules for a few vulnerabilities. This figure illustrates the performance of Panda. We set the execution time limit of each smart contract to 15 minutes during the experiments. It can be seen from the figure that most smart contracts can complete the detection within the time limit. The next is the most interesting part. We use Panda to conduct a vulnerability assessment on all smart contracts on the Algorand blockchain. The 3 tables show the evaluation results. From the experimental results, we know that these vulnerabilities are prevalent in Algorand smart contracts, revealing the urgency of identifying and preventing some such vulnerabilities. Okay, let's get into the case study. In this case, I give a simplified code for the smart signature that includes vulnerabilities for unchecked transaction phase and the unchecked transaction parameters. This code is vulnerable because the group size is not a fixed value, and at least one of the transactions whose parameters have not been validated. In this case, I give an example code of a smart contract that includes both arbitrary update and arbitrary deletion vulnerabilities. The reason for the vulnerability in this code is apparently due to a programming error by the developer. To be specific, there is no correct constraint of the incomplete parameter. Okay, during the evaluation process, we found that a large number of smart signatures used an incorrect way to call the validator. As shown in the figure, the logic of these smart signatures restricts the validator's application ID, but does not restrict the uncomplete parameter. Therefore, an attacker can use the opt-in or clear state transaction to bypass the validation logic. This is because the validation code in the validators is not executed when processing these types of transactions. It is worth mentioning that the Panda tool also reported many smart contracts with such vulnerabilities, some of which have large deposits. We also helped the developers to fix the vulnerabilities and received a bug bounty. That is the end of my presentation. Thanks for listening.